Okay. Oh, that's all right. At that one. Okay, so I guess I better sit closer. We're going to go through active circuits, analog, and then digital. And I also have a little addendum I did at the end of stuff that I didn't remember to talk about in part one. So let's see how it goes. We always have to talk about vacuum tubes because they're still around. There's questions on the exam about triode tubes and pentode tubes. And basically, it was the first sort of active device. Fleming invented what we today call a diode, where it could pass current from one element to the other in one direction only. And then later, I think it was Lee DeForest that added a control grid, and they discovered that by applying a voltage on the control grid, they could actually control the current flow. So that really became the first amplifier device, and also as a switch, well, mostly used as amplifiers. Today, most everything is based on semiconductor technology. And if you remember when we talked about the free electrons in material, the valence electrons that were on the outer shell that weren't tightly bound, they discovered that if they took a material like silicon, which is normally not a conductor, and they introduced some impurities, typically they use boron or phosphorus, they could create a material that had either excess holes or excess electrons. So it was either a positive charge or a negative charge. They discovered when they put two of these pieces together, a p-type and an n-type, it would act like a diode, just like in the Fleming valve, and it would conduct current in one direction from anode to cathode, the conventional current. The electron flow goes the other way, or charge flow. Because of that barrier between the two, there's a little bias voltage or an offset. There's another name for it, which I forgot at the moment. But typically, it's from 0.6 to 0.7 volts for silicon diodes and 0.3 for germanium diodes. Most diodes that you're going to run into are silicon-based. So everything is going to be in the actually 0.6 range. I think one of the exam questions is 0.7 volts. Most everything says 0.6, but the ARL is always right. What I did here was to simulate a typical 4001 diode, which is, I think, a 1 amp diode they use as a rectifier mostly. And this D2 is a perfect diode, the kind that don't exist, and plotted them. And you can see on the perfect diode, it started conducting here at 0 volts. And that slope of that line is just due to the 10 ohm resistor. If you see on the real diode, if you look down here, it's about 0.6 volts where that curve starts. And then the slope of the line is slightly less because you have some internal resistance in the diode in addition to the 10 ohms, which is why they're not perfectly parallel. Any questions so far? Okay. For people that aren't familiar, here's a collection of modern diodes, the symbols that are used to identify them on schematics, which are also exam questions, what they physically look like. So your standard diode is just a filled-in triangle with a line representing the cathode. On the physical device, not sure you can, well, on the second one, you can see there's a black stripe, and that's how they usually mark small diodes, with a stripe to indicate the cathode end. Some of the bigger ones tend to be bullet shaped, and the pointed end is the cathode. When we get down here to light emitting diodes, it's the same symbol with a couple little arrows indicating the light being emitted. There's a picture of a typical one. They come in almost any color you can think of today. We have photodiodes, which work just the opposite. So we have the light going into it, and they have a little window in the case so that light can get to the semiconductor wafer. It actually turns out that all the devices are photosensitive. And they discovered that, and they can enhance these so they're more sensitive. But if you could put the regular diode in a clear case, it would be affected by light. We have a Zener diode, which is another exam question. And they discovered that if you reverse the polarity on a diode, it won't conduct up till a point where you get a breakdown voltage. And they discovered by the way they make the material, they could control that breakdown voltage or the Zener effect. So they can do these at a whole range of voltages, 5, 10, 12, pretty much whatever you want, and use them as a simple voltage regulator with a resistor. You got Schottky, which has a lower voltage offset on it. And that's not a test question that I'm aware of. Nor tunnel diodes, the kind of special purpose. Laser diodes are used in a lot of things nowadays. They're about, the small ones like in the picture are usually about 5 milliwatts, and they can either be set to generate just a single dot, or with a little lens on there, they'll generate a line. So you can use them, like particularly in a laser cutter with a couple of those on there with a cross. You can actually, and on milling machines and other things, you can use them for alignment. There's a current regulator diode, which I don't have a clue what that is. Maybe Byron does. I've never seen it before.
No, I've never seen the symbol before.
Yeah. And then there's varactor diodes. Another behavior of diodes in the reverse direction is they have capacitance. And they discovered that the reverse bias voltage could control the amount of capacitance. So you can actually use it as a voltage controlled capacitor. And it's used for as a tuning element, or for FM generation as a reactance modulator, which we'll talk about later.
The definition of a current regulating diode is a device that maintains constant current flow despite voltage fluctuations.
Okay. Did you look that up or did you know that?
No, I looked it up.
Okay.
It's the
It's
power.
not a test question, so, but it's good to know.
Wouldn't that be good for charging like lithium batteries?
Possibly.
Because they want constant current fluctuating voltage.
Okay. One of the primary uses of diodes is to convert AC to DC. So here I typical circuit with a 60 cycle, 60 hertz wave coming into the transformer. I think I set it up as a step down. I don't remember. Simple diode and a load resistor. And if we plot that, you'll see that the diode is conducting on the positive half cycles of the AC waveform. So what you get is what we call pulsing DC. If you filter that out with basically a low pass filter or integrator, you can smooth it and get almost a constant DC.
So the voltage will be the same through the diode. It'll come in at, let's say, 10 volts AC and come out 10 volts DC because it's only taking a half wave.
It's going to be less than the peak.
Okay.
In fact, it's going to be, well, it's going to be the square root of the peak or the RMS of this part squared plus the DC offset squared, whatever that is in this case. You don't need to know that, but it will be a lower voltage than you started with, definitely.
Okay.
Which is one of the reasons why we go to two diodes called full wave rectification. In this case, it requires a center tap transformer. So we conduct, or we get each waveform, each half, because these are 180 degrees out of phase. So in this case, you can see that the yellowish line is doing every half cycle. So there's twice as many pulses per second, so it's easier to smooth it out and filter it. Then we can go to a bridge rectifier because you can save money by not having to have a center tap transformer, which had to be twice the voltage. In this case, it's the same transformer we used in the first example with a half wave. And in this bridge rectifier, there's 4 diodes in a bridge formation. So you would have, if I can draw it right, one like this. One like that. And these would just be the opposite. I think I'm doing this right. Right?
Yeah. I think so. I haven't looked at a bridge rectifier schematic.
Yeah.
And
these come in a package already formed, so you don't have to, put 4 diodes together. Oops. And again, you get the same kind of every half cycle. Now, if you notice, there's a little more loss than there was on the full wave. because of the resistance in the diodes. And there's also, it's because of the range, it's hard to see the 0.6 volts, which would be down here to pass the threshold, which is why you see this little flat spot. That's because it's not turning on at 0 volts. Okay, so now that we got a diode, somebody decided, well, why don't we make it like a triode tube and add a third element? So if we take and put two N-type pieces of semiconductor material with a P-type in the middle, we have the diode plus another one, and it turns out that the current between the P-type and the N-type, which would be the emitter, and the P-type would be the gate, will control the current flow between the collector, which would be the other N, and the emitter, which is N on the opposite side. So it makes a little sandwich. Now, later they discovered that they could build a transistor that acted much more like a vacuum tube, in that they could control it with a voltage instead of a current by creating an electrostatic field, which would have sort of a pinch effect and control the amount of current flow. Here's an example of what we call a bipolar, which uses current as its control mechanism. And as you can see here, the P element is the base, and we apply a current through there between the base and the emitter. And that creates a current flow, or allows a current flow between the collector and emitter. And it's proportional to the amount of current going from base to emitter. But there's a gain factor of 100, 200, something like that. And that's what we use to make an amplifier, take advantage of that gain. The symbol for a standard bipolar transistor is over here on the left-hand side, showing the base, emitter, and collector. They tend to make, when they produce these, they're not symmetrical. And if I remember right, the emitter portion is larger than the collector portion, so it's not symmetrical. Point that out because when we do a field effect transistor, they are symmetrical, and it doesn't really matter whether you switch the source and drain around. They work the same way. So
on a radio, the gain knob, is that what's controlling the current through the transistor?
Maybe not directly, but yes.
Okay.
So voodoo cells basically work on a bipolar junction, if I'm
Right.
correctly.
Yes. Here I'm just showing a typical sort of test circuit for a bipolar transistor. And you normally, in the data sheets for transistors, you will see a plot like this where they vary the current through the base at specific points and show what the voltage is across collector to emitter, so that you can figure out how you want to bias it, so you can kind of determine what voltage you want to operate at, how much current you want to pass through it, and then you pick your load resistor, which is this line here, and the slope of that's the value of the resistor. So normally for like a Class A amplifier, you would want to bias it so that it's normally operating with no signal right here in the middle, in between what we call the cutoff and the saturation. And cutoff means that at that amount of input current on the base, there's no current flowing from collector to emitter. In saturation, you've got the maximum amount of current flowing. So there's very little resistance between collector and emitter. And when you're actually using a transistor as a switch, you set it up so that the input current either puts it at this point or this point, off or on. I did a simulation of a typical 3904 NPN transistor. It's a very common one. It's used in all sorts of stuff, been around for years. And you can see the blue line is the collector current, and the yellow line is the gate. Oh, I got a G there. Should have been the base current. And the scales are opposite sides. So at the cutoff point, we've got 0 amps flowing on the collector. At saturation, it's up here at 10 milliamps, and that's limited by this 1K resistor across the 10 ohms, 10 volt source. And you can see what the equivalent base current is at those points. And in this case, for saturation, it's about 70 microamps. So if you do that division, you can see what the gain is. The bottom plot is showing the voltage versus the base current and how it goes from when the transistor's off, you've got 10 volts, and when it's on, you're almost down to 0 volts. Won't quite be there because there is some internal resistance. Okay, the next type is the field effect. It still uses the doped N and P material, but it adds another element which is insulated from the body so that we can create an electrostatic field across this material. Around here. And by making that a negative voltage across there, you can pinch off the current flow from the drain to the source or source to the drain because they're really symmetrical. The typical symbols are over here on the left. The only real difference is the direction of the arrow. Now, there's also a bunch of other types like MOSFETs and variations of those, but they all work pretty much the same with a electrostatic field that controls the amount of current flow. There's a picture of typical transistors from power transistors, which are in these bigger, I believe that's a TO3 package. The smaller ones are typically in these little plastic, is that TO92, I think, if I recall. You see one of the, what do they call these? It's not exactly a flat pack, and it's not it's almost a surface mount. It's a little bit bigger than some of the really small ones. These with the tabs on them are also power transistors. And that's how they get the heat out. You attach that to some sort of heat sink because they do dissipate a lot of power unless they're in switching mode. Okay, so one of the basic building blocks that we need to build radios and transmitters and other electronic equipment is an amplifier. So we either use a transistor or a vacuum tube or electron tube, or a valve, as they call it in England. And there's essentially 4 classes of amplifiers. A class A, which I talked about, where you would bias it in the midpoint, has the lowest efficiency, but it has the highest fidelity. In other words, it will almost 100% reproduce the input signal. But because of the low efficiency, it takes a lot more power and generates heat. They came up with a class B configuration, and it's normally 2 transistors, similar to when we saw the full wave rectifier, only with transistors. So each transistor will amplify one of the peaks, the positive peak or the negative peak. There's a little crossover because of the same 0.6 volts across the base to emitter, just like in a diode. So there's a little distortion, but it's much more efficient. Class C, they typically use in things like transmitters to get the efficiency. And it requires a tuned circuit on the output because it's only passing a portion of the peaks of the waveforms, and it requires the tuned circuit to resonate in order to sort of rebuild the AC wave. So it has to be tuned to the frequency that you're operating. And then there's class D, which some people call digital class. It's not really digital, but it does use sort of a digital technique in that you feed the analog signal in to a pulse width modulator. So you get square waves of varying width out of it, depending on the input voltage. And those are easy to amplify digitally, and then you run it through filters to get the audio frequency back. They typically only use these in lower frequency audio work.
You know about sticking bandpass filters on the end of it?
Low pass filter,
Okay.
low pass. We're not the filters yet. We'll talk about them. Okay, here's a class A that I threw together, and it actually seems to work. Been a long time since I designed an amplifier. It's set up for a gain of 6, and you can see the input waveform versus the output waveform. You notice there's a 180-degree phase shift, which is fairly typical, but there's no distortion that you can see. That's one of the advantages. And that's why you'll see Class A amplifiers in a transmitter for the audio section, for instance, before a speech compressor.
So distortion typically either shows up as ripple or clipping.
Yeah. And I have the thing to talk about the effect of clipping coming up.
Okay.
But in this circuit, basically, you're using the R2, R3, and R4 network to establish the bias point, which is about in the middle, which would be around 6 volts. And you normally use a little emitter resistor that helps stabilize it. It does a offset voltage. That's a pretty standard configuration. It's one of the things I learned in college decades and decades ago. Now we're going to do the same thing with a junction FET. And the only real difference is the way you bias it. And the fact that you've got to make it go negative in order to turn it off. We still have the phase inversion between the input and the output, but it's a class A and we still get high fidelity. I believe one of the test questions on the exam is about how well it represents the input for a class A amplifier. Okay, now we hadn't talked about these, but this is just a package of a number of transistors, and we call it an operational amplifier. It's a differential amplifier. So any signal between this plus and minus input gets amplified by maybe a factor of 10,000. So it takes essentially, 0 volts between these two to generate an output. So if you use a feedback loop, and you have a voltage divider at this point, which will establish the gain. In this case, the 10 and the 2 is a third of the total value. So the gain would be 3. Okay. 20 and 10 is 30 ohms. And we're at 10 ohms. So we're 1/3 of the divider. Okay. So if I've got 1 volt coming in here on the input, when this output gets up to 3 volts, I'll have 1 volt on this side and they'll be balanced again. So the thing about dealing with operational amplifiers is you assume that both of these are 0 volts or virtual ground. And it makes it fairly easy to figure out the feedback resistor. And again, here's just a plot showing. Now, in this case, because we came in on the positive input, there's no phase shift. So this is a non-inverting amplifier. You could do the same thing by coming in on the negative side and make it an inverting amplifier. Okay, the next block are oscillators. We have fixed frequency, usually a crystal control or a packaged one where we can generate, in a lot of cases, it'll output sine wave, triangle, sawtooth, and square all at the same time. Or it can be an LC or an RC feedback network to generate a fixed frequency, where neither of these are variable. We have variable frequency oscillators, usually in a tuning circuit for a transmitter or a receiver. And there we have either an LC circuit with usually a variable capacitor. It's harder to vary the inductor, so it's a lot easier to get a variable capacitor. And you can use things like varactor diodes, which are even smaller, and you don't have a physical capacitor with plates that you got to turn and a mechanical thing. And the newer ones, we have direct digital synthesized, which uses some digital techniques to actually generate a sine wave by referencing a sine wave stored in a fixed memory, all the different samples of a sine wave. So you just look those up and output them and then filter it with a low pass filter again. And then digital clock signal generators, which is usually a crystal controlled oscillator. And they're normally, they come in small packages where you just supply usually 5 volts to it and you get a signal out of it. To make an oscillator oscillate, there's this thing called the Barkhausen criteria. You don't need to know that. It basically says for it to oscillate and maintain oscillation, you have to have an overall loop gain of 1. Okay, so it means you have to compensate for any losses in the feedback network with enough gain in the amplifier so that the overall gain is 1. Now, in order to start oscillation, you've got to have higher gain for it to actually start. But if it maintains higher gain, it will stop. I proved that many times in my simulator and trying to get an oscillator to oscillate. Here's an example of what they call a twin T. It's using 2 different phase shift networks, a low pass and a high pass, to generate the feedback. And I'm not sure in this one, other than I think it's this capacitor here that actually allows it to start oscillating, because it acts differently once it's charged up than when it first starts. But as you can see in the simulator, it actually started and oscillated. I had many attempts where I couldn't get it to oscillate. We can do the same thing with our operational amplifier. In this case, one of the little nonlinear elements is a little light bulb, a little pilot light, because it has variable resistance. So it changes the feedback gain. It does not do a sine wave. It's not exactly a triangle wave either, because you get a little rounding, but it's probably because I have too much gain in there. The other thing we can do is buy a thing called a monostable or astable multivibrator. The typical one you see is a 555 or some variant of it. And it works by charging up this capacitor that you add through this resistor network that you add, which gives you a RC time constant. So however long it takes to charge this capacitor affects the period of the waveform. So, and it's set internally with the trigger value. So as it starts charging up, when it gets up to the trigger point, it discharges it and then starts all over again if you configure it as a astable multivibrator. They can also be configured as what we call a one-shot, a monostable, where it will just produce 1 pulse every time you trigger it. And the width of the pulse is again going to be determined by this RC network connected to